Hello everyone. In this video, we are going to talk about line extraction algorithms from the data of range sensors like LiDARs, ultrasonic, and so on that are used in mobile robots. Like previous robotics videos that I had on mobile robots, the material here is coming from this amazing book, Introduction to Autonomous Mobile Robots by Sigwart, Nurbach, and Scaramuza. Amazing book. So what do we have here? So if you have your mobile robot going around some room or any space indoors or outdoors, and it has a LiDAR on it, and this LiDAR, as you know, it is going to scan the walls and it will give you an angle theta and a distance rho. So using rho and theta, you can basically determine a bunch of points, right? So what it will give you is only a bunch of points. The question is now, if you want to say where the walls are exactly, right, or windows or anything else. So here, let's say we are looking at the top view. So these are the walls or doors or anything. So where are these lines? Okay, how many lines are there? And what are the parameters of these lines? Okay, because all you have is a bunch of points. So for instance, in this case, when I have these points, I can say there are only 2 lines, or I can say there are 3 lines, and this guy may be an outlier, some noise in the data. Okay, so which one of these would you pick? And how would you parameterize those? Now, once you have a line, you can, of course, parameterize a line, but the major question is how many lines are there? Are there 2 line segments? Because you might say this is one line, this is one line. Could I say these 2 are the same? I can merge them or not merge them or something. So this is not a super trivial problem. And in general, if you look at the literature, there are 6 major algorithms that you can use for answering these questions. The 3 fast ones that I'm going to focus in this video are called split and merge, incremental, and line regression. These guys, if you look at them on a good computer, in terms of the speed, they can be implemented at very fast speeds like 1500 hertz, 600 hertz, and 400 hertz. So they are really good for real-time applications. Now, their precision is not bad, and there are algorithms that have better precision like ransack, like half transform, and the expected maximization. These have better precision, but their speed is quite a bit lower. They are not, I mean, the ransack is not bad, but maybe depends on how fast you want your system to detect these walls and everything. Maybe 1 hertz is not enough. Now, the other thing about this more precise method is they also provide more false positives. So that is not good. This is the good part for them. This is the bad part. So you want it to be fast, less false positives, and more precise. Now, of course, you cannot have fast and precise both go up at the same time. It's always a trade-off. So for real-time applications, we want to do the ones that are very fast. They don't do a lot of false positives, and their precision is not too bad. So in that case, for instance, you see that incremental seems to be relatively a very good one. And their complexity in terms of their parameters is given here. I don't want to focus on these right now, but in general, there are 2 categories. The fast ones, less precise, the more precise ones that are slower and give you more false positives. Now, half transform, I have 2 videos on that, how to do it in MATLAB, how to do it in OpenCV, and I also talked about the theory of half transform. How do you detect all different lines? So half transform, I have completely covered on my channel under playlist image processing and computer vision. Okay, so that one is completely taken care of. In this video, as I said, I want to focus on these 3 fast ones, and then hopefully in another subsequent video, I talk about the ransack and this expectation maximization. So these 2 we'll keep for another video. Let's focus on these 3 fast ones. So what do we have? Split and merge. How does this algorithm work? So let's say here you have this bunch of data, these data. And how would you split and merge? So if you look at here, if I want to, this is the overall algorithm written in English, but in general, if I want to tell you how it works, first thing is you have to decide n, the number of points that you want to put in a line. So let's say here, for instance, in this case, I go with, I don't know, 6, 7 points. Every 6, 7 points, I fit a line to them. So here, that's what I did, right? In this case, I guess it's like 9 points. So to these 9 points, I fit a line that is this line. And then to the other 9 points, I fit another line that's this other line. Okay, so here like n was 9, for instance. So first, I fit every 9 points without overlap. I fit a line to them. Good. Now what? Now that you detected these lines, now you go and say, well, let's look at these 9 points and see between these 9 points, which one of them has like the maximum distance, or find their vertical distance from these lines, because the line will not go through all of these points, right? Each one of these points, if you look, they have some vertical offset from the line. Okay? And here you pick a threshold, dp, those points for which the distance between the point and the line is bigger than dp, you might detect it as a corner point or as a breakpoint. That might be a place where one line finished already and another line started, but still you are counting them as one line. So you say, well, guess what? Here is where that line should have ended. That is where this distance here is bigger than dp. So let me stop here, not count the rest of it. So I'm gonna ignore the rest of the points after this. And only from the beginning to that point, now you're gonna fit a line to only these guys, and there we go, you get this line. You do a similar thing for the other line, and you find this to be like a breakpoint or a corner point, so you only fit a line to this. In that case, now you have what? You have 4 points that, or 5 points that do not belong to anything. So you have to repeat the same thing for these 5 points. Okay, first, because your n is big, you're gonna fit one line to all of them, or you might fit 2 lines to the, but by the way, this n you can change during the algorithm if you want, or you can keep it fixed. So here, for instance, to these 3 points, you can fit 1 line, to these 3 points, you can fit 1 line, and then again, if you find that, hey, well, actually, there are breakpoints again, like here and here, then maybe you don't want to do that. You want to fit 1 line here and 1 line there. And then at the end, when you have these line segments, if these line segments share the same parameters or very close to each other, now you go ahead and merge them. So you have this line and you have this line, and you merge them and you get this one here. Okay? So here, based on, again, the closeness of the parameters describing these lines, you can merge them or decide not to merge them. So that is basically how this split and merge is working. And you see the algorithm is very, very simple. Okay? Now, we also have incremental one. What is the incremental? So here, first, you pick 2 points and you fit a line to the first 2 points. Then you bring the next point and add it to the current line and recalculate the line parameters by line fitting. Here, the important thing is you have to provide a line condition. If by adding this the new point, your line condition is still valid, you keep adding another point and recalculate the line parameters and recalculate the line condition, see if it's true or not. As long as it's true, you keep adding more and more points. When the line condition is false, then you stop and you start a new line. So here, if you look at it, First, I started with these two, and guess what? This line is good. Then I brought the third point, and I fit a line again, and guess what? Again, you see that this line and the previous one are almost the same parameters. The change in parameters is not too much. You might say, what kind of line condition would you have? Probably one thing you can have is some of the squared errors or some of the squared deviations. Okay, so these 3 points now fit a new line between them. Now the line might not perfectly go through them. They have the distance. When you add them together, let's say as long as this is below some threshold, I say this is still a good line. And then I bring another one. Again, guess what? I have another one. It's good. Okay, so still the line condition is valid. Now when I bring this, now, because this point is way off from the rest of them, the new line fitted is going to be this. And now, guess what? You have now a bunch of vertical displacements. And when you square them and add them together, now they're going to go above some threshold. So I know now that I passed the threshold for some square deviation. Guess what? I added a point to the line that was not really a part of that line. My line changed big time. Okay, and for that reason, I know that this is not a good place to add a line here. Okay, so in that case, what do? I say, well, guess what? These points that I had, they were one good line. When I added this, that was not a good idea. So what do? Now I go back to step 1 and I start with 2 points. Which 2 points? The last point and this new point. And I fit a line to them again. Okay, it's a good line. Now I bring another one. And this time maybe I have to pass this kind of line. If some square differences is above the threshold, again, maybe that's not a good point. So I say what? I say, well, that green line was a good one. I'm gonna stop it, and now I'm gonna start the next one again with the point of previous one, and then this one, and then again I fit a line and bring more and more, and incrementally, basically, I form lines. So I start with line 1, and then line 2, and then line 3, and so on. So this is incremental. You start with 2 points, you add more and more points until the line condition is still valid. Whenever it's violated, you finish the previous line, you grab two new points, one from the last line, one the new one that start mismatching, and you fit a line and you keep going. So this is the incremental one, and you see the difference between this one and previous one. Okay, the previous one, every n points you fit a line, you split, and then later you merge. But here you kind of start from the beginning and keep going. And also we have line regression. So what is line regression? Let me talk about this as well. So in line regression, which is, I can show you a picture of that as well here, but I would rather do it with my MATLAB code that I wrote for it. It says, again, you pick a sliding window of size NF. So this is similar to the N. To every NF consecutive points, you fit a line. So if I want to do something similar to that previous one, so let's say, for instance, here we had this kind of data, right? So pick some NF, whatever you want, maybe 4, maybe 3, maybe 5, whatever. That hyperparameter changes the final results, of course, okay? This threshold that you pick, these n's, this dp, these hyperparameters will change the final result significantly. So they have to be fine-tuned to the environment and to the sensor. If your sensor gives you tons of readings, then maybe you can use bigger n's. If your sensor only gives you a few points, then you have to use a smaller n's. If your walls are long, you can allow more points. If there are lots of small walls with small line segments, then maybe you have to bring down the number of n. The same goes for threshold. Threshold is depending on the noise. If your sensor is very noisy, then I have to use bigger thresholds. If my sensor is relatively accurate, then I can use a smaller threshold. Okay, so it depends on the environment, it depends on the sensor, and also how fast your robot is doing its job. These parameters have to be fine-tuned to get the best result. So what would you do here? Every NF points you do it, so maybe every 3 points. So here I come and fit one line here, right? And then maybe one line there, and then maybe one line there, and I keep going, correct? So every 3 points you start adding something. And here, again, you have to create a line fidelity array. How would you create this line fidelity array? So here, what you would use is the Mahalanobis distance, which is between every 3 adjacent windows. So between every 3 of these, you will calculate a Mahalanobis distance. And since on my channel, as far as I looked, so far I have never introduced the Mahalanobis distance, and this distance is used a lot in machine learning, deep learning, computer vision, robotics, and so on. I want to briefly talk about this distance moving with the rest of the algorithm. So what is this? Mahalanobis distance is a distance between a point and a distribution. Remember, in one of my previous videos, I talked about a distance between one distribution and another distribution, the KL, the Kullback-Leibler divergence, okay, or Jeffrey's divergence. That was between 2 distributions, but this one is between a point and a distribution. So if I have one point here, and I have some distribution of points, let's say, for instance, some kind of Gaussian, right? And here we are looking in 2D. So I have some distribution here, and this distribution has some center, and it has a covariance matrix. And covariance matrix, of course, the eigenvalue of that will give you the spread of this ellipse, and it has some centroid, right? Something like this. So if I want to calculate a distance between this point and the points in this distribution, how do I do that? Answer is the Mahalanobis distance. So how do you define it? If this point is shown by x and that distribution is shown by 2 parameters mu and s, then it is the square root of x minus mu transpose s inverse x minus mu. If you look at it in a 1D, it is going to be like x minus mu squared divided by sigma squared, and then under the square root, which is basically x minus mu over sigma, right? That's kind of like a z-score that you have in normal distribution, correct? Which if it's more than 3 or less than -3, that means mostly you are an outlier. So you see that's very similar to the z-score that you have in 1D. This is just for any dimension. Mu could be any, and here instead of a single number, you are using the inverse of a matrix, the covariance matrix. So you see it's like a generalized z-score, basically. That's what it is. And it measures basically how many standard deviations the point is from the mean of the distribution, adjusted for the covariance of the data, because the covariance of the data will determine that standard deviation. So that is the beauty of this, and it has lots and lots of applications. You, as I said, you definitely use it in outlier detection, okay, in multi-dimensions, in classification and pattern recognition. You use it again to see whether a point belongs to a class or a cluster or not, right? So you can do that. And again, related to outlier detection, you can use it to see if there is any event is an anomaly or not. For feature scaling, you see basically what you're doing here is a scaling. So you can do it for feature scaling and engineering. Mahalanobis distance can be used instead of the original feature. And of course, in robotics and controls, You can use that to assess, for instance, how far a robot current state is from a desired state when you want to consider the uncertainties in your calculations and the correlations between the state variables. So if the state variables are not correlated and there is no uncertainty, you don't need it. But you know, there is always uncertainty, there is always correlation, and sometimes correlation between the states, but definitely always uncertainty. In that case, instead of a simple Euclidean distance, it's better to use the Mahalanobis distance. Okay, so now that we know what Mahalanobis distance is, between each three adjacent windows or line segments, we calculate this value, and then if it's bigger than some threshold, then we keep them separate. Otherwise, we can merge them together. Okay, and then you're gonna see the result in my simulations. So here it was a brief discussion of these three fast algorithms, and you see the reason that this line regression is a little bit slower than the two other is because of calculating the Mahalanobis distance. Okay, that's why it is not as fast as the two others, especially the split and merge. So here is the code that I put together, and here I simulated some data that resembles like a LiDAR scan with like three walls. And then here you can see the split and merge algorithm. It has some parameters. This is that important DP parameter that you can change. It will affect the result and the speed of it big time. And then you have the line regression algorithm. The NF that I'm using is 5. There are two thresholds here, one for the Mahalanobis distance, the other one for merging. You can change those as well. And finally, you have the incremental one, which again, it has a threshold again for merging. So let's go ahead and see what we have over here. So this is the data with some noise of three walls. This is the line, the split and merge. And you see as these lines are forming and they are merging to the best that it can based on the threshold we provided. Then we go with these line segments of line regression. And then the merging is happening based again on the threshold that we provided. And then we have the incremental. Okay, so you might say, well, incremental looks quite a bit faster than merge and split. It is because the way we pick the thresholds. If I go back and for this merge and split, I change this 0.05 to 0.1, you're going to see it's going to be extremely fast. Just the animation is not going to be that easily visible, but let's take a look. There we go. Done. So it really depends on what parameters that you're choosing that will change the final result, right? So here you see these are the merge line segments. And this is, of course, the incremental one. So it really depends on those hyperparameters. I'm going to share this file for you under video description, give you a download link. Feel free to play with it and learn from it and change the parameters. And hopefully you learn how these first three fast algorithms are working. So I covered these three now. And as I said, I have also covered the Hough transform for you. So now I can say I only owe you one more video, and that is going to be on ransack and of course the expectation maximization. I will make a separate video on that, I promise. Thank you so much. I'll see you in the next lecture.